In the previous video, what we did is we talked a little bit about how capacitors discharge, and the idea behind that was to really get a sense of like how does the current change as capacitors are discharging through a light bulb. Capacitors are really, really good at storing energy, and they are good at storing charge. And they're used a lot of times in applications where you might need a little bit extra boost of current because you don't have enough available in terms of a battery or some motor that's running. So a common application is actually in cars. When you have sort of a high-end stereo and you have subwoofers and things like that, when the music is turned up really loud, the amount of energy that's needed to drive those things is more than your car can provide through its battery or through the alternator. And so capacitors are there to sort of drive a little bit more and provide a little bit more energy to drive those electronic components. So what we're going to do in this video is we're going to talk a little bit about how that idea works. That is, how do they store charge and what kind of energy do they actually store when we have them. So we're going to go back to an example that we had before of two parallel plates that both have an area of A. They're separated by a distance d, and across one of them there's a charge plus sigma, and across the other one there's a charge minus sigma, and those mean Q over A and minus Q over A. So the idea there is that we talked about conductivity, and I know that we talked a little bit about that it might be confusing to bring in conductivity and surface charge in the same situation, and we're not going to do that. So the context should make it pretty clear. Now, what Michael Faraday did was he set up situations like this, where he had parallel plates with particular areas separated by certain distances. What he found was that for a given set of plates, for a given distance apart, that the quantity, there was a quantity that remained constant. So when he dumped a certain amount of charge on those plates, they would have a certain potential difference across them. And the ratio of those two things he found to be a constant for a given configuration, given area of plates, given separation. And it was consistent. It was something that he continued to find. This constant we actually call the capacitance. And we're going to derive sort of what that is and why it happens to be constant in particular kinds of situations. So in the case of this setup that we have here, we have two parallel plates that are really big compared to the separation between them. And so the electric field between them is actually a constant, right? So the electric field that we would expect between them is the surface charge per unit area. As a result, we can think about the potential difference across those plates as basically being the electric field times the distance, because it's a constant. The electric field is a constant value. So the potential difference across those plates is going to be the electric field times whatever their separation is, which in this case is going to be sigma epsilon naught over d. So now we have the potential across the plates. What about the amount of charge that's sitting on those plates? Well, we've set them up with a situation where we have a charge density of sigma. So the total charge on any one plate is going to be equal to sigma times the area, that is the charge density times the area. So in this case, we're going to have Q is going to be the charge density times the area. So the ratio of those two things, which we are referring to as the capacitance, is going to be equal to then sigma times the area divided by the quantity sigma d over epsilon 0. Or, as the sigmas cancel out, epsilon 0 times the area times d. Now we can see exactly why what Faraday observed was what we would expect from this simple model, right? The capacitance only depends on the geometry of the situation, and by that I mean it only depends on really A and D. That is the area of the plates and how far apart they are. So if Faraday fixed the size of the plates, fixed how far apart they are, you would expect for most situations that the charge that you dump on the plates and the potential difference would be linearly related through this capacitance. Now this is an important thing because the idea here is that this capacitance is essentially a measure of how much charge you can stick on the plates for a given potential difference. So from an engineering side of things, you can modify the size of the plates, how far apart they are, for your particular application. That is, if you need a whole bunch of charge or you need a large voltage, you can modify these things as you see fit to be able to provide that charge or that voltage as you need it. This is a really nice application. Now, in modern electronic equipment, parallel plate capacitors are not what are actually used. Oftentimes, the sort of standard ones are actually rolled like a snail shell. So there's this two plates sort of like coupled together and sort of rolled around really tightly. Other ones are much more complicated than that, but these are sort of the simplest idea. These are still parallel plate. They're just rolled up in some way. We can further modify them by putting some materials in there, but we won't talk about that in any detail right now. Okay, so how is all of this stuff related to the energy that these capacitor plates can store? So the way to think about that is to think about if these plates have a potential difference across them, they're already charged up, how much more energy does it cost to put a little bit of charge on there? And that relationship is essentially the electric potential energy associated with putting a very little bit of charge at a given potential difference across the plate, right? So dumping a little bit of charge dq at a given potential difference onto the plates. Now that potential difference, we have already derived it. We know what it is. And in fact, what we're going to do is we're just going to set this up to say, well, how much energy does it take to charge the plate up entirely, okay? So the game we're going to play is that this potential difference, which we have derived up here, is sigma epsilon naught d, which means that for a given amount of charge that we have, it's going to be more like little q d epsilon naught a, okay? Where q is just the little amount of charge that we're thinking about here, okay? So ultimately what we have is a relationship between the energy and the charge that we're putting onto these plates. So I'm going to clean up this stuff because we've sort of exhausted all we need here. And we have some of this stuff down here that we'll leave. But the idea being that if we look at the little amount of energy that we're going to get by putting an additional amount of charge, dq, on there, it's exactly equal to d epsilon naught a times q dq. Okay? Now what we're going to do is we're going to take the capacitor and we're going to say, well, we'll start it off at 0 charge, and we're going to ramp it up and we're going to dump a total amount of charge, capital Q, on it, right? That was what we had when we started up this situation. We had a total amount of charge on it. So as we charge this thing up, what we're going to find is that we can integrate this. So assuming that there's no charge to begin with, we can assume that there's no potential energy, and there will be some total potential energy associated with the end situation. And so what we're going to end up integrating is a constant times this function here, q dq, which is an integral that we know how to do, right? That's 1/2 little q squared, evaluated at the endpoints. Okay? So what that's going to give us is that the total energy associated with taking a capacitor from no charge to a total charge Q is equal to some constant, d epsilon naught a, times 1/2 big Q squared. Now one thing I'll point your attention to is this guy right here, that constant that we're keeping track of, is exactly 1 over the capacitance. So ultimately, the relationship between the energy and the charge and the capacitance is that the total energy that we are storing on a capacitor is 1/2 the total charge on the capacitor divided by its capacitance. And so we can start to see exactly how we can get energy in this situation by dumping more charge on it, or by changing the configuration of the capacitor so that it has less capacitance. The less capacitance it has, the more potential energy you're actually storing on that capacitor. So what we've done in this video is basically talk a little bit about how the capacitance is defined, exactly how we were able to understand why it is a constant from these sort of geometrical properties, and then what kind of energy gets stored on capacitor plates when we charge them up.